Hello ladies and gentlemen, welcome to our new lecture, new topic. Now we're moving to more practical approaches of modeling, and we are moving to most basic class of models that we'll be using, that is linear models. And linear models are based for almost all statistical modeling that's happening and of course we can there's more complicated model, but the intuition that we get on linear models will help us later in order to do some more stuff. So what are we generally going to do? We'll discuss first some theory. That will be the first video. Then I'll do more extensive case study of one data set creating multiple linear models and how such models are created. There will be a second part, or maybe second and third, and we'll end with a last part when we'll create a more complicated model using functions of predictors and showing how you can easily create very complicated relationships using linear models. So let's start now with linear models, and let's start with getting some kind of intuition of what we're going to do. Generally, it is known along both machine learning community and statistical community that linear models are not necessarily phenomenological models, or machine learning models are not phenomenological models. They are quantitative models. They get you precise they give you values, but they don't give you the causal relationship between one another. That's why in some parts of the literature they are called so-called geocentric models. Why geocentric models? Geocentric models, or really geocentric idea of universe, was that Earth was the middle of the center of the universe, and everything rotates around the Earth. Some politicians still believe that it is still possible. There is some debate on that. However, we know that it's not true. But people who were thinking so were very ingenious people. They were thinking, like for example, Ptolemy, the Egyptian astronomer from the almost 2000 years ago. And the idea of geocentric model was based on they observed sky, they observed movements of planets, of stars, and based on that, Earth is in the center of the universe. There would be problems to justify these observations. So they created a model that, under these assumptions, still provided the proper values. They created this model by constructing a very complicated geometrical structure of so-called epicycles. They were adding epicycles that were representing the movement on the orbit of Earth, was additional movement around of a moving center of a circle which the planet was moving around. This is the epicycle. And this adding of epicycles allowed you to compute the values that are consistent with observations. So their model were causally wrong, but were very accurate. They provided good predictions of where planets will be, and that were consistent with previous data. And this is what's going on with very practical statistical models or machine learning models, that you create models that use previous data in order to obtain the quantitative prediction of values of interest. And this, what are you doing? So, coming back to the Ptolemy, it's important to note that his idea of adding epicycles is not completely without sense. Using modern mathematics, you could express that you have a periodic orbit that you are observing, a periodic movement, and adding epicycles is really equivalent of extending representation of this movement with a Fourier series, which is a very good method of approximating periodic functions. So the idea wasn't completely without merit, but it doesn't express the causal relationship. It only expresses it gives you the predictive power. And what really we'll be doing is called regression. The regression is a complicated nomenclature because representing regressions either in statistics or in machine learning, so as you can get some confusing statements, especially there are certain interpretation to the word regression or to regress to something that can be counterintuitive. Really, regression models are used to explain the relationships between independent or observable variables and dependent variables, something that we are interested in. And we want to get that relationship in form of a model that will allow us to create predictions. And really, in machine learning, for example, but here we'll be very consistent with it, regression models are models that give you a value, a real number that you get from the data. So if you are interested in a real number, you are creating a regression model. If you are interested in an integer or binary value or something, then the situation becomes more complicated, especially if you have a selection of from a limited set of values, then you have a classification problem. And then you do not have a regressor but a classifier. Classification problems are really more the domain of machine learning, because in statistical modeling we are more interested on the estimating the probability of belonging to a class, and this is still a regression model, but constrained to a probability spaces. But in case of the machine learning, then you can split the problem into classifiers. So this is what we're interested in. And around linear regression, the most important aspect, at least in most basic cases, is the Gaussian distribution or normal distribution. Because this distribution allows us to quantify our uncertainty about the measurements and about our predictions. And we'll be using normal distributions for such purposes, but not only normals. And we are assuming that this normal distribution has a mean, traditionally denoted by mu, and the standard deviation of sigma. In Bayesian speak, we can say something like this: we are uncertain about value of y, so we don't have, the y is not a random number sampled from the distribution. Y is something of interest. We are uncertain about this value, and our uncertainty is expressed by normal distribution. So we know where means of that distribution is, what is the spread of the distribution, or the standard deviation in this case. This is what we know. We don't know exact value, but we have certain idea of where this value is located, and we can express by probability where this value is located, better or worse. So this is why Gaussians, this is why we are using Gaussians. Of course, we can use different distributions, but Gaussians are very convenient with those two parameterization and some other stuff. We already encountered Gaussian distribution in a Newcomb experiment, and we've seen also that you can replace Gaussian with, for example, student t distribution. And student distribution is a very good distribution for certain purposes, especially for so-called robust regression, when the, for example, the outliers are present in our data. But this is something that we can return later, or you can study on your own. Either way, what really we want to do? We want to create a statistical model, and we want to find the description of our uncertainty about the problem in order to make predictions or inferences about this problem. However, statistical models, whatever we want to do, still encode only that information. Still, statistical model is a computer program that we use. This is kind of function that we've encoded in our in our software. We've estimated the parameters of this model using probability distribution, or we just use our model as some consistent Monte Carlo simulation that gives us the give us our values, but they do only what we've encoded to them, and only based on the data that they are given. There is no artificial intelligence. Never. There is no such thing as artificial intelligence. It's always data and assumptions that give you the predictions, and of course implementation. But assuming that implementation corresponds to our assumptions and provides our data, it gives you values. So statistical model or any kind of model or other model is just that, a robot that gives you give him a question that is consistent with his parameters and it gives you answers. If your question is inconsistent with the parameters, you get strange things. Garbage in, garbage out. And in Bayesian framework, we generally get models that are in the form of probability distributions. Everything in Bayesian models has a probability distribution. And this encapsulates our uncertainty. And this is important in this aspect because we can capture how our uncertainty is influencing our predictions, our inferences. We can use it later, for example, in order to give uncertainty to our decisions. So if we want to, for example, create an utility function that will provide us certain, for example, profits from our predictions, we can infer what will be values of this utility depending on our uncertainty. So we can propagate the uncertainty from the start of the model, our model, to our decisions. So we could get certain uncertainty about the results. So this can be very, very useful. In case of different kind of models, you will just get numbers, and those numbers not necessarily will be able to predict your losses after if something is inconsistent with your predictions. So why Gaussians in this case? Because Gaussians are generally easy to manipulate, easy to calculate, and they are almost everywhere. Because Gaussian distribution arises from addition. All of you have heard about certain limit theorem that generally a sum of any independently identically distributed random variables is normally distributed. So if you are sampling from certain distribution, you get and you add the results will be normally distributed. So for example, let's consider a football field. Football field in European style football, or as we call it, new football. We have the white line for the middle of the field. Let's put a person in middle of the field and tell him, well, make 16 steps along the line, randomly choosing however you wish, how long steps as you wish, but just stay on the line. You can go one direction, you can go other direction, but stay on the line and do 16 steps. And then we record that person's position at each of the steps, and of course the final position. So we are interested in what are the positions, what is the distribution of the positions. And like for convenience of modeling, we can assume that this position is that this movement is uniform. So we are sampling from the uniform distribution on the -1 + 1 interval. So that gives us the movement. That person can stay in place or just move from one leg to another, or just move. So what do we have here? Here we have the positions from up to -16 + 16. That's assume meters or full steps, whatever we call that. And that this is our maximum range, because that person can, from the beginning at the middle of the field, can move maximally 16 steps from to one side or the other. And as we can see, we simulated this 1,000 times, and we can see what's going on, that generally people are wandering in all of the directions. So After 4 steps, we can see that there's certain concentration in the middle. Of course, less people decided to move all the way through the 4. Again, this happens with 8 steps and 16 steps. And in 16 steps, as you can see, the normal distribution fits it very well, because we've observed that situation. The positions, the addition of these positions step by step leads us to the normal distribution, to the number of steps in each of the directions. The actual position, some of it will be normally distributed. The more steps we take, the more central limit theorem takes effect, and the distribution will be even more similar to the Gaussian. So really, normal distribution is very natural in such cases, and in any case that you see naturally that the data came from some kind of the addition, then, or subtraction, but generally a summing operation, then the normal distribution is natural. But of course, there's also other situations. So of course, processes coming from increments are normally distributed. What is also interesting, if you observed small percentage changes. So for example, 1% movement of 1% this way or 1% in the other way. So generally, multiplication by numbers close to 1, these will also be normally distributed, which is a special case of situation when you generally have multiplications, because multiplications of numbers leads us to the normal distribution, but on a logarithmic scale. For very small, for numbers close to 1, really we can very well approximate log normal and normal with one another. But with this multiplication of generally by numbers, then you get the if you compute the logarithm of the function, the logarithm will now then, instead of series of multiplications, will be a sequence of additions, and these additions will be normally distributed. So on the logarithmic scale, you will receive still the normal distribution. So normal distributions are in many cases present present in many places. So that's why they are backbone of the computation. And of course, because they are easy to compute, and because of that, lots of things we want to approximate with normals. Because we approximate with normals, then we get very nice result. We'll be able to get the nicely computable results, and that is was very important, especially before we could do some more advanced computation. But it still is important, because this advanced computation takes a lot of time. So let's consider the algorithm of constructing a model. First of all, we need to recognize set of our measurements that will determine our outcome. So we'll have the values that we'll use as predictors for our model. Then we need to define a likelihood. Likelihood, that is plausibility of individual observations. In other words, how our observations fit with our model. And in linear models, it is usually Gaussian. Then we want to choose from our available measurements which we will be using to predict our outcome. So which will be our predictors. Then you need to find some way of relating the likelihood distribution to the predictor variables, and this will be actual our model creation, so how will we get that consistency. And through that we'll define the model parameters, which we'll then choose priors for, and of course then having such models with likelihood and priors, and the structure will be able to infer the parameter values. In case of general linear models, especially with Gaussian distributions, we have the following formalism. Our outcomes will be distributed by normal distribution. This normal distribution has one important thing, that means of the distributions will be individual for each of the outcomes. But these means will be represented as linear function of predictors. In this basic case, we have the one-dimensional. We have one predictor, and the mean will be consist of an alpha, which is called an intercept, and beta times the value of predictor. And we then assign certain priors, and certain, depending on the situations, priors might be different, but generally we like to use normal priors for alpha and beta coefficients, unless there are reasons for not to do so. This actually is very closely related to something called ridge regression from machine learning. That is the regularized regression. This generally makes our parameters stay in reasonable ranges. It just needs a lot of data to move away from reasonable values. And we'll use some kind of regularizing distribution for standard deviation. And this will generally, exponential distribution is very nice for this purpose, because it allows small values of standard deviations, but still has enough tail that you can move away from that if data justifies it. As you can see, mean is parametrically related to the predictors. So, and this is related in a linear function. And this is where linear models take their name from. That means are linearly related to the predictors, and especially with respect to parameters. Parameters are presented linearly. So there are no functions of parameters. There might be functions of predictors, but we are not interested in that too much, because we will see that later. But really, what we have here, that our parameters are represented linearly, and this is very important for our computation later and construction of our model. And why actually this linear function is so good? Because we could expect really that everything is nonlinear. And this nonlinearity is true. Life is nonlinear. Every aspect that you know to be linear is linear only in a certain range of application. For example, in electrical circuits you have Ohm's law. Ohm's law relates your resistance, the voltage drop on the resistor is equal to the multiplication of resistance and current, which is a linear model with respect to both current and resistance. However, the problem is that this, of course, works if it works. Because if you have a very small resistor and you apply a large current for it, for example, you take a resistor that can be found in a child's toy, and so you take that resistor and you put it through the current of, for example, 100 ampere. You won't have the the observed drop of voltage as would be consistent with this resistance and the current. The resistors will evaporate because of the heat. You will have your model won't be working. Your model won't be applicable, because all linear models are really applicable only locally. So our models are local, and they can be justified by Taylor expansion. If you remember linearization from, for example, control theory courses, you know that we can approximate nonlinear functions for applications with linear versions of them. And of course, if there was a nonlinear relationships between predictors and parameters, we can always approximate it using Taylor expansion as a linear function of predictors with new parameters that are related to original parameters in some way. But that is not a problem, because those new parameters are also present linearly here, because they are not dependent on the predictors, only on the original values of parameters. So we can get those parameters here. So our model locally will work. We won't have these relationships between, for example, alpha and theta explicitly, but value of alpha and value of beta will be enough for us in order to do some predictions that will be locally. Of course, you need to remember that linear models are local. And if you read some statistical literature, or especially popular literature on using statistics, you will see trend lines, like linear models that extend to giant spread of values of predictors without any checks of that linearity. But you need to know that these models are local, and because of that, they have the certain limitations, and extending them might be difficult in certain cases. So, if we know all that, we can start moving to the actual modeling to see what's going on, and we will start with a very simple anthropological model, which I will tell you in a moment, in the next video, and that will be covering the heights and weights of certain ethnic group called exclamation sign Kang, which are living in the edge of the Kalahari Desert in Africa, which are a very isolated group, so they are very interesting for some kind of analysis because there will be no heterogeneity in these dataset. But that's enough for now. Thank you, and see you in the next video, where we will discuss the